lecture on 12.7 this morning, and 12.7 is the beginning of the part of the chapter that's on the take-home test. When I give you the take-home test, if you kind of have the take-home test out and you watch this video simultaneously, there's probably going to be things in this video that will help you with the take-home test quite a bit. And sold myself a little short here. This section, the author could have made this section right after section 12.2 before he did some of the stuff that we did in the last section where he had to multiply to do probabilities. In this section, we won't have to do any multiplying to do probabilities. We're going to be able to answer all the probability questions either by creating a sample space or just understanding the problem and forming fractions based on numbers that are obtainable from the problem without having to do any sorts of multiplication. So just like the last few videos, there's homework problems and then there's the problems I'm going to do on the video. There aren't any homework problems that aren't like an even problem, so I don't have to do any of the homework problems as I do this video. So I'm just going to start into the section, and as I get into the problems, I'll explain the section, hopefully decent enough. You'll definitely want to have a book handy for this because there's some pictures that aren't that easy for me to duplicate just because of the colors in the pictures. So I'm going to start off looking at the first group of problems that are homework worthy. And for you, that's problems 5, 7, and 9. Problems 6, 8, and 10 are, they're the same sorts of problems as 5, 7, and 9. So I'll read through the problem so I understand the problem, and then I'll answer the questions and explain what makes this section different than the last few sections. So in problems 5 through 10, there are 6 circles. There's 2 yellow circles, a green circle, and 3 orange circles. And then we're assuming that maybe these circles are written on slips of paper that I put in a hat, and I throw all the 6 different slips of paper in a hat, and I pick out one of these circles. And I want to find the probability, and there's new words in here. So I pick one of these circles, and I know some information about it, and knowing extra information is going to change the denominator of my probability as well as maybe the numerator of my probability. So for problem 6, I have these circles. So there's a yellow, and the yellow ones are 1 and 6. And there's a green 2, an orange 3, 4, and 5. And in general, if my experiment was to put these 5 numbers, 6 numbers in a hat and pull one out, my denominator would in general be 6, and the numerator would be however many numbers have the characteristics that I'm looking for. So the probability 6, it starts off saying, what is the probability that I get a 3? In general, I would say it's 1 in 6 because of the 6 circles, one of them's a 3. But that wouldn't be correct for this particular problem because for this particular problem, the author gives me extra information. The author says, I'm telling you something about the circle that I picked. This extra information is going to impact both the numerator and the denominator of my answer. If this was the question, is just in general, what's the probability of getting a 3? I would have said 1 in 6 because of the 6 circles, one of them is a 3. So without any additional information, if this part wasn't given, the probability of picking from one of these 6 numbers and getting a 3 is 1 in 6. But that's not going to be the case. That's not the answer to this. This given the circle is yellow tells me I need to construct or imagine a new sample space, because I know that I picked a yellow circle, which means I've either picked the 1 that's yellow or the 6 that's yellow. So now the question is, what's the probability that I get a 3 if I've picked from this? So now I'm pretending that I know that the circle is yellow, so I've picked, I know that I've picked one of these two. The denominator is going to be 2 because there were only 2 different circles that I could have picked that are yellow. And the numerator is going to be any one of these circles that satisfies the criteria. In this case, it satisfies it being a 3. The probability is going to be, there's no 3's there, so it's 0 and 2. It's impossible. So if I tell you for sure that I've drawn a yellow, it's impossible that I've drawn a 3 because the yellow was orange. We try to do 8. 8's probably going to be the same sort of problem. So the beginnings of number 8 says, what's the probability that I've drawn a number less than 2? And if this was the problem, without any information after this, there's 6 numbers that I could choose from. Of the numbers that are, there's only one of them that's less than 2 because the number 1 is less than 2. That's not the answer to this problem. Just like 1 and 6 isn't the answer to 6, 1 and 6 is not the answer to 2. In general, the probability of getting a number less than 2 is 1 in 6 because there's one number less than 2 out of the 6. But when the author puts this extra words after it, the extra words is given the number is less than 5. So the author's telling me something about what was drawn. I need to construct a new sample space based on what could have been drawn. So without any information, I could have drawn any of the numbers between 1 and 6. But now I could have only drawn a 1, 2, 3, or 4 because I'm given that the number is less than 5. So given that I've picked a 1, 2, 3, or 4, what's the probability that I've gotten a number less than 2? So in my answer to this problem, the denominator is not going to be a 6 because I know I didn't pick the 5 or a 6 because the 5 and 6 aren't less than 5. And of the numbers that I could have drawn, the 1, 2, 3, and 4, how many of them are less than 2? One of them is less than 2. Oh, should be 1 over 4. Sorry about that. So my denominator gets crunched because there are only 4 numbers that I could have picked. And of the 4 numbers that I could have picked, one of them is less than 2. So the answer to number 8, in general, would be 1 in 6. The chances of getting a number less than 2, which is the chances of getting 1. A 1 is 1 in 6. But with the extra information, my denominator changes. In this case, my numerator doesn't change. Whereas in the last problem, number 6, both my numerator and my denominator changed with the extra bit of information. So for each of the problems that I'm going to do in this section, if extra information is given about what's happened, that's going to impact possibly both the numerator and the denominator and could very well change my probability. This section is called Conditional Probability because I'm given an extra condition, I guess an extra bit of information to help me compute my probability. So 10 starts off saying, what's the probability of getting a number greater than 3? And if that's all that it says, well, a number greater than 3 would be getting a 4, 5, or 6. There's 3 numbers that are greater than 3 out of the 6 numbers. If this was the entire problem, I'd say the probability is 3 and 6 are 1 and 2. Because there's 3 numbers greater than 3, the numbers 4, 5, and 6 out of the 6 numbers that I could have picked. But there's extra information, so that's not the right answer. The extra information says given the circle is yellow. So I need to imagine a restricted sample space. So to do this particular problem, I need to construct or imagine a new sample space based on the information that I know. And I'm told for certain that the circle is yellow. So in my problem, the yellow circles were the 1 and the 6. So the denominator for the answer to problem 10 is the number of circles that could have been picked based on the extra information. In this case, because I knew I drew a yellow circle, the denominator is going to be 2. And then the numerator is going to be anything that in the sample space that's greater than 3. The number that's greater than 3 is the 6, so the probability is going to be 1 and 2. Coincidentally, it came out to the same probability without the extra information, so that extra information wasn't helpful. But in the other problems, the probability went from 1 in 6 to 0, or 1 in 6 to 1 in 4. So sometimes the extra information will change the probability as compared to if the extra information wasn't given, and sometimes we'll get the same probability. Okay, so now I'm going to jump down to the next problems. And the next problems involve picking from these 7 figures. There are 2 yellow figures, 3 pink figures, and 2 blue figures. There's circles, triangles, and squares. So in general, picking a number, picking one of these numbers, there's the 7 would be my denominator. If I'm not given any information and I'm asked to compute a probability, there's 7. I'm picking one of these things. There's 7 different things to pick from. The denominator would be 7. So let me, organize my information the best I can. So right here I have the number 1, which is yellow and in a circle. 2, I guess is pink, or maybe the author's going to call that red. I'm just going to call it pink. Pink, and it's in a triangle. And then 3 is blue, and it's in a square. And then the 4 is pink, and it's in a square. 5 is yellow, and it's in a circle. 6 is blue, and it's in a triangle. And the 7 is pink, and it's in a circle. So I'm going to pick one of these at random. 12 says, what's the probability of getting a circle? And if this is all that 12 said, the probability of getting a circle in general would be 3 and 7, because there's 3 circles from the 7 figures that I could have randomly picked. So I'm picking one of these at random. If the problem didn't have any information, the problem of getting a circle is 3 and 7. But I have extra information, and the extra information is given that a number greater than or equal to 5 is selected. So the colors aren't so important in this particular problem. So for each of the problems that I have a given, I need to construct a new sample space. So 3 and 7 is not going to be the right answer. My new sample space, so I know that a number bigger than 5 is selected. To answer this question, I have to restrict my sample space to the 5 that's in the circle, the 6 that's in the triangle, and the 7 that's in the circle. Because I'm given that a number greater than or equal to 5 is selected, so I know that the 5, 6, or 7 is selected. To answer this question, the denominator of my probability is going to be 3, because there's only 3 different figures or numbers that could have been selected. The numerator is going to be 2, because of these 3 different numbers, there are 2 circles. So for each of the problems in this section, if after what they're asking me to find there's a given, I have to imagine a new sample space and calibrate my probability based on only things that could have happened. So 14 says, what's the probability that I get a red? So this pink is supposed to be red. That pink is supposed to be red. That pink is supposed to be red, and they're not actually pink. So what's the probability that I get a red or a blue figure? And in general, if the problem stopped there, there's one red, two reds, three reds, and two blues. If the problem said what's the probability of getting a red or blue figure, in general, the probability would be 5 or 7 if I was able to look at the entire sample space from the original problem. The word given is going to crunch down my sample space. So given that an even number is selected, so I need to construct a new sample space, and my new sample space is only going to contain the even numbers. The even numbers are the red 2, the red 4, and the blue 6. So the fact that I'm told an even number is selected, I know that the 2, the 4, or the 6 had to be selected. So the restricted sample space based on the given information is going to contain those 3 figures. The probability of getting a red or a blue figure is going to be 100%. The denominator for this probability is going to have a 3 because there's only 3 figures that I could have picked. And of the 3 figures that I could have picked, there are 2 reds and 1 blue. They're all either red or blue. So I'm going to get a 3 out of 3, or 100%, or a probability of 1, as opposed to 5 or 7 without the extra information. 16 is a similar problem. It first asks what's the probability of getting a circle. If the problem stopped there, the answer would be 3 and 7, because there's 3 circles of the 7 figures. But that's not going to be the answer because there's extra information, and the extra information is given that an even number is selected. So once I have a given, I make a new sample space. This is a friendly problem because it has the same new sample space as problem 14 because it has the same extra given. So the new sample space for this particular problem is the red 2, the red 4, and the blue 6. What's the probability I get a circle if one of those 3 is drawn? The denominator is 3. That's the number of items that could be drawn. The numerator is the number of circles within these 3 items, which is none. So the probability would be 0 and 3 with this extra information, or 0. So it's going to be impossible. There's no chance that I've drawn a circle if I've drawn one of those 3 figures. So problems 11 through 16 really aren't any different than problems 5 through 10, other than the sample space is different, but the idea is the same. The author gives me information about what's happened in the experiment, and that new information is probably going to impact my probability. In order to compute the probability, I need to construct the sample space that's implied by the given. The denominator is going to be the number of items in the new sample space. The numerator is going to be the number of items that have the characteristic that we're looking for. So I'm restricting my sample space based on extra information that's been given to me. (17 through 24) involves spinning this wheel one time, and what could happen is it can come on any of the numbers between 1 and 12. Let me write down the numbers that could come up, and I kind of organize them by color. So this wheel, if I do it properly, for problems 17 through 24, it has some blue figures. Those are the numbers 1 and 8. It has some yellow figures. Those are the numbers 3 and 10. It has some red figures, or red numbers. Those are the numbers 5, 6, and 7. and it has some purple numbers. Those are the numbers 2, 4, 9, 11, and 12. If I go to problem 18, it starts off saying, what's the probability an even number, that the spinner lands on an even number? If this was the whole problem, the denominator would be 12 because there's 12 even numbers that are on the wheel. And of the, there's 12 numbers on the wheel. And of the numbers on the wheel, they're the 2, the 4, the 6, the 8, the 10, and the 12. There's 6 evens. So if the problem didn't have a given, I'd look at all the numbers on the wheel. There are 6 even numbers of the 12. My answer would be 6 and 12. But because the author gives me extra information, the author says, given the color is red, and that answer won't be right, I need to construct a new sample space. So I know that a red has come up, and the red portion of the red numbers on the wheel are 5, 6, and 7. So this probability, the denominator is going to be the 3, because in my sample space that's relative to the given information, there's 3 values, 5, 6, and 7. And of those 3 values, there's 1 even, the 6. So the answer to 18 is going to be 1 and 3. When I go to do number 20, it asks, what's the probability that a number greater than 4 is spun, and then given, and I won't even pretend to answer the question without the given. I'm just going to do the given in this case. Given the color is red. So it's nice that the author gave me the same given. The fact that the color is red means that either the 5, 6, or 7 has occurred. So the denominator in this particular problem is going to be 3, because there's only 3 numbers that could have came up. Because the number is red, there's only 3 red spots. So my new sample space contains the numbers 5, 6, and 7, which are the red numbers. The numerator needs to be all of these numbers that are greater than 4, and all 5, 6, and 7 is greater than 4. So it's going to be 3 and 3, which is going to be 1. 22 says, what's the probability that I get an even number? Same question as 18, but probably a different answer than 18 because the given that's different. And then the given for this is, given the color is red or purple. So I need to get my new sample space. My new sample space is going to contain any red or purple, which is the 5, 6, and 7, that's red. And the 2, 4, 9, 11, and 12 that are purple. So my denominator for this probability question is going to be 8, because there's 8 numbers that are listed here. There are 8 numbers that are the 3 reds and the 5 purples. Now I want, from this new sample space, I need to find out how many evens there are, because I'm trying to get the probability of getting an even. So the 6 that's red is even. The 2 and the 4 that are purple are even, and the rest of the numbers in this new sample space are odd. So I'll say that this probability is 3 and 8. Didn't say I was going to do 24, and it kind of works out well because it doesn't fit on this page, and I want to look at the sample space again. So I've done banks of problems 6, 8, and 10 parallel to 5, 7, and 9. 12, 14, and 16 parallel to 11, 13, and 15. And now my 18, 20, and 22 parallel to your 17, 19, and 21, and 23. Now I'm going to move to the next group of problems. And in this next group of problems, I'm going to have to construct a sample space because I'm doing 2 things as opposed to 1. So the first group of problems where I was picking one of those circles, The second group of problems where I'm picking one of those figures. The third group of problems where I'm spinning the spinner once. I can imagine the sample space without having to write it down. When I get to this fourth group of problems that I'm going to work on, I can't imagine the sample space because I'm doing something twice. And I think we've done a sample space like this before. So in this problem, some bills are put in a hat. For a $1 bill, a $5 bill, a $10 bill, and a $20 bill. One of each are put in a hat, and two bills are selected with replacement, and then I'm asked to construct a sample space, because in order to answer probability questions when you have two things going on as opposed to picking one, spinning the wheel once, or picking one of the colored figures, it's harder to imagine the sample space. So I'm going to write the sample space down for problems 25 through 28. So the sample space for problems 25 through 28, without any information, it says I'm putting these bills in a hat. I'm picking a bill, and there's one $1 bill, there's one $5 bill, there's one $10 bill, and there's one $20 bill. So this is going to be my first bill selected. And then it says with replacement. So if I pick the $1 bill and then put it back in the hat, when I go to pick a bill again, I still could get that $1 bill along with the 5, the 10, or the 20. So for my second bill, it could be a 1, 5, 10, or a 20. And my sample space will start to be getting a $1 bill first and a $1 bill second, a $1 bill first, a $5 bill second, a $1 bill first, a 10 second, and a 1 and a 20. Done with that, I'm going to go to the 5. If I get a 5, I can still get a 1, 5, 10, or 20 for my second bill because I'm putting the $5 bill back. The with replacement part of this allows me to get the same bill twice. If the author would have written without replacement, then I couldn't have got the same bill twice. But this branch is going to give me a 5 first, then a 1 second, a $5 bill, then a $5 bill, a $5 bill, then a $10 bill, and a $5 bill, then a $20 bill. Done with the 5, now I go to the 10, then I go 1, 5, 10, and 20, and then a $10 bill, then a $1 bill, a 10 and a 5, a 10 and a 10, and a 10 and a 20, and then with the 20, getting a 21st and a 1 second, a 21st and a 5 second, a 21st and a 10 second, and a 20 and a 20. So the sample space has 20 elements, 16 elements in it, and when I go to answer probability questions, my denominator is 16 unless I have to restrict the sample space. Problem number 26 says, what's the probability that both are $1 bills? In general, it would be 1 in 16, because of the 16 combinations here, there's only one that has two $1 bills. But I need a restricted sample space because I have this extra information. And the author gives the extra information as using the word if as opposed to the word given. It says if the first is a $1 bill. So I need my new sample space because I'm given extra information about what's happened. I'm given that the first is a dollar bill, so that one of those has happened. That either I've got the 1 and a 1, a 1 and a 5, a 1 and a 10, or a 1 and a 20. So given that the first bill is a 1, there's 4 numbers that can go in my denominator, and of those 4, there's one that has the double 1. So the extra information takes a probability that in general would be 1 in 16. The probability of getting 2 1s is this one spot out of the 16 things that could happen. The extra information gives me a new sample space, and within this sample space, there's 4 things, and one of them has the desired outlook. Let me try to sneak 28 in here. 28 says, what's the probability that both bills have a value greater than 5, which means a 10 or a 20. But I have extra information that's going to give me a new sample space. It says if the second bill is a 10. So I'm going to sneak my new sample space in. That extra information allows me to reduce the sample space. I'm told that the second bill is a 10. All of these have the second bill of 10. So my new sample space is getting a 1 then a 10, a 5 then a 10, a 10 then a 10, or a 20 and a 10, because all of those have the second bill being a 10, and that's the extra information that's given. My denominator for the probability in number 28 is going to be 4. My numerator is going to be anything in this new sample space that has both bills greater than a 5, and that's those two items there. So I'm going to say the probability is 2 and 4, and I'm going to reduce that to 1 and 2. So if this was an odd question, then I could check an answer in the back of the book. The author would give me a 1 and 2 for the answer. So this problem, these two problems, 26 and 28, are supposed to help you with your problems 25 and 27. Next problem, I'm rolling 2 dice. Rolling 2 dice, just like picking 2 bills, needs me to have a sample space constructed. We constructed a sample space for rolling 2 dice before. I'm just going to write that sample space down because I can create that sample space without doing a tree. The tree is almost a nuisance to me. So I'm going to start working with problems 29 through 34. It says 2 dice are rolled one after another. I'm going to do the sample space. And what can happen is the first dice can be a 1. The second dice can be a 1. The first dice can be a 1. The second's going to be a 2. So this is the sample space that I need for problems 29 through 34. If I'm not given any extra information. So I can get a 1, 1, a 1, 2, a 1 then a 3, a 1 then a 4, a 1 then a 5, a 1 then a 6, or a 2 then a 1, a 2 then a 2, a 2 then a 3, 2 then a 4, 2 then a 5, or a 2 then a 6, or a 3 then a 1, a 3 then a 2, a 3 then a 3, 3 then a 4. This is a nuisance to do, but you need to have the entire sample space listed in order to answer probability questions, or in order to be able to restrict the sample space. So I'm doing this without a tree because I can imagine this sample space. I'm familiar with it, so I'm constructing it without a tree. And there's nothing, it's probably better to not do a tree for this if you can do this. So there are 36 items in this sample space. In general, if I'm asked probability questions about rolling 2 dice one after another, 36 is my denominator. In most of these problems, 36 won't be my denominator because I'm given extra information and I need to restrict or make a new sample space. 30 says, what's the probability that the sum of the 2 dice is 6 given the first dice is a 1? So I make my new sample space. My new sample space is going to be anything from the original sample space that has a first dice a 1. That's going to be the entire top row. My denominator for this is going to be 6 because there's 6 different things that could happen if the first dice is a 1. Now it says the sum of these. So I'm going to sum this. The sum of 1 and 1 is 2. The sum of 1 and 2 is 3. The sum of 1 and 3 is 4. The sum of 1 and 4 is 5. The sum of 1 and 5 is 6. The sum of 1 and 6 is 7. Of the things that could have happened in my new sample, restricted sample space, there's only one of them that has a sum of 6, so the probability is going to be 1 in 6. 32 says, what's the probability of getting a sum of the 2 dice to be an even number given the second dice is a 2. This is the part of my sample space that has a second dice as a 2. So the sample space that I need to use to answer this question is going to have 6 items. So 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, and 6, 2. I'm worried about summing these. The sum of those is 3. The sum of those is 4, 5, 6, 7, and 8. To do this probability, the denominator is going to be the 6 things that could have happened in my restricted sample space. The numerator is all that have an even sum. 3 of the 6 have an even sum, and I'm going to reduce that to 1 and 2. And then 34, getting a sum of 7 or 11 given the first dice is a 5. That's this. So the sample space that I'm looking to do the probability in problem 34 is the 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, and 5, 6. The denominator is going to be 6 for this probability. I'm going to sum all of these. I can do those in my head pretty quickly. I just added the 2 dice up and got 6, 7, 8, 9, 10, 11. My goal is to get a 7 or 11, and there are 2 ways to get a 7 or 11, 1, 7, and 1, 11 out of these 6. So the probability is going to be 2 and 6, which I'm going to reduce to 1 and 3. So my answer for 34 would be 1 and 3. Up until problem 34, I can construct the sample space if there's 2 things happening, like picking 2 bills, rolling 2 dice. The first group of problems up through 24, there was only 1 spin or one number that was picked, and I can visualize the sample space. So up through 34, constructing or seeing the sample space is friendly. The next group of problems, everything after problem 34, the author gives me tables, and answering the probability questions via tables, I think it's going to be a little bit harder. For some students, it's not going to be any harder, but for some of you, it's going to be a big jump. So hopefully I can make that jump tolerable. So what I've just done, I did 30, 32, and 34, and that's supposed to help you with 29, 31, and 33. So now I'm going to do 2 table problems. The first table problems is going to help you do 41, 43, and 45. And that's going to be my 42 and 44 are supposed to help you do 41, forgot to write 43 as a homework problem, and 45. So these problems, 41, 43, 45, as well as 41, 42, 43, 44, 45, and 46, they all based on this table. In this table, students at a zoo were asked whether they'd prefer a lion or an elephant, I don't know, as a pet or to go see, I'm not sure what it is, but the information is given here. 200 boys were surveyed, 90 preferred lions, 110 preferred elephants, 160 girls were surveyed, 75 preferred lions, 85 preferred elephants. There were a total of 165 kids that preferred lions, 195 that preferred elephants, total of 360 kids, 200 boys, and 160 girls. So I have to kind of familiar myself with, oh, I see, now I read the problem. If the zoo were to get 1 additional animal, would you rather have them get a lion or an elephant? Now that I read the problem a little closely, now I understand. So 90 boys of the 200 boys said, let's get a lion for a new animal. 110 of the boys said, let's get an elephant for a new animal. So now I understand the question at least. So now I'm going to answer probability questions. There were 360 students surveyed. If I'm not given extra information about the students surveyed, the denominator is going to be 360. So what's the probability if I asked one of these kids that the kid selected they wanted the lion. So the child selected the lion as the new animal that they wanted. Notice there's no given that or if that. When this is the case, I don't need to restrict the sample space at all. I'm considering all 360 kids, and of all 360 kids, 165 of them preferred the lion. My answer to 42 is going to be the 165 kids that picked a lion out of the 360 kids total. Didn't bring my calculator this morning to reduce this, so I'm going to hope that you can reduce this via your calculator, divide them, do math, enter, enter, and it'll give you a reduced fraction as opposed to that big fraction. 44 says, what's the probability that the child selected a lion? And then I have given that. And the given that is going to restrict my sample space or restrict my denominator. It says, given that the child was a girl. The fact that it says the child was a girl, I can only look at the girl line. And the girl line of this says there were 75 girls that preferred the lion for the new animal, 85 girls that preferred the elephant for the new animal, for a total of 160 girls. So when I go to answer question 44, I'm only worried about this part of the sample space because I know for sure that the child selected was a girl. The denominator for this probability is going to be 160 because there were 160 girls that were surveyed. The numerator for this probability is going to be the 75 girls of the 160 that preferred a lion. So the given that restricts the portion of the table that I'm looking at to contain the given information. 42, because it didn't have a given that, I looked at the entire table. There were 360 child or children of the 165 that wanted a lion. 46 says the child selected as a girl given the child preferred a lion. So I'm going to restrict the sample space to the lion column. So the lion column, because I know the child wanted the lion, so I'm restricting myself to look at only this part of the sample space. So there were boys, girls, in total. There were 90 boys that preferred the lions, 75 girls that preferred the lions, for a total of 165. So in problem 44, because I was given that the child was a girl, I took the girl row from the sample space and used it to compute my probability. In this problem, I was told that the child preferred a lion, so I took the lion column of my probability. Now I'm going to answer the question. There are 165 kids that preferred getting a lion for their next, and of the 165 total, 75 of them were girls. So the probability in 46 is going to be 75 in 165. All of the fractions that I have on this sheet you should reduce. I can attempt to reduce this, but it might be bad. If I divide this by 5, 75 divided by 5 is 15. If I divide 165 divided by 5, I get 33. So that would be 15 over 33 for an answer. Similarly, if I did this last problem, reduced it by 5, 75 divided by 5 is 15, 160 divided by 5 is 32. That would be better answers for 44 and 46. And you could also reduce the answer for 42. Way easier to reduce via a calculator than without a calculator. So I get to do 2 more table problems, and this next table problem starts to show the age of the book because it talks about renting VHS tapes and DVDs back when there used to be Blockbusters. Now there really aren't any Blockbusters, and back when you had your choice of renting DVDs and VHS tapes. So this particular, there's a survey. 300 people were surveyed that were renting a movie from a Blockbuster, and they broke them down by age, if you're under 30 or over 30, and then they asked you what you were renting. So some people rented DVDs, some rented VHS tapes, some rented both. And so this table basically breaks down by age and what you're renting. DVDs, tapes, I guess you guys have to know what tapes are. VHS tapes are both. So now I'm going to answer the questions, and the denominator of my probability is going to be 300 unless I have a given that. So when I go to problem 48, what's the probability that a person that was surveyed was 30 or older? There isn't any extra information that is a given. So the denominator is going to be the 300 people that were surveyed. And of the 300 people that were surveyed, 180 of them were 30 and older. So the answer to problem 48, because I don't have a given that, then the denominator is going to be all of the 300 people that were surveyed, and of the 300 people that were surveyed, 180 were older, 30 or older. If I reduce this reduces to 18 over 30 if I hack out a 0. And if I divide by 6, 18 divided by 6 is 3, 30 divided by 3 is 10. Or 30 divided by 6 is 5. So that should be 3/5. For 50 and 52, I only have to either look at a specific row or a specific column. So 50 says rented both videotapes and DVDs given the person was 30 or older. When I look at problem number 50, I'm only going to look at the row for 30 and older. So when I go to answer problem 50, what's the probability that the person rented both videotapes, I'll say VHS tapes and DVDs, and then given they're older than 30. So I need to only look at the portion of the table that relates to older and 30 or older. So we've got only DVDs, there's 64, only videotapes, which I'm going to abbreviate VHS, and there's 94, both, which there's 22, in total there's 180. So this is the portion of the table I'm asked to look at for this. There were 180 people 30 or older that were surveyed, and of the 180, 22 rented both. So the answer to this unsimplified is 22 over 180. If I divide by hand, 22 divided by 2 is 11. 180 divided by 2 is 90. So the answer to this is going to be 11 and 90. 52 says, was older than 30. So what's the probability that the person was 30 or older, given they rented only videotapes? I'm abbreviating that VHS. So now for this, I need to do the only videotape column, and that column has an under 30, 30 or older, and a total. The under 30 and only videotapes were 39. The 30 or older were 94. And the total was 133. So I'm only looking at that portion of the table because I was given that information. The denominator is going to be the total number of people that only rented VHSs, which is 33. The numerator is going to be that I can't read. It's supposed to be 94. The 94 in that column that were 30 or older. And I'm not sure that that fraction reduces. It could reduce, but I don't have a calculator with me, so I don't think it reduces. But maybe it reduces by 11. No, I just don't think it reduces. So 94 over 133 is probably a good answer for that. Okay, so that problem should help you when you do 47, 49, and 51. So this is going to pair up with this 40 and that. Let me do 60, 62, and 64 just to help you through the last problems. So 60, 62, and 64 have to do with an inspector checking light bulbs. So 59 through 64, I have a table. The table, an inspector checks a light bulb, and she checked 20-watt bulbs, 50 and 100-watt bulbs. Some were good, some were defective. Most were good, not as many were defective, and it gives me a total. So 60 says if we pick a light bulb, what's the probability it was good, given that it was 50 watts? To do this problem, I have to look at only this row of the table, because I'm given that it's a 50 watter. So the denominator for problem 60 is going to be the 105, that is what light bulbs that were 50 watts. The numerator, I'm only looking at this line. So for number 60, the probability that it was good given it was a 50 watt. I'm only looking at the 50 watt row of this. And of the 50 watts, there were 100 goods, 5 defective, for a total of 105. My denominator is going to be the 105 50-watt bulbs that I could have selected from, and the numerator is going to be the 100 good ones that are in that batch. 62 says good given that it is 100 watts. So the part of the table I need to look at is the 100-watt row. And in the 100-watt row, there are 120 good, 10 defective of the 130. The probability that it's good, given that it's 100 watts, there's going to be 130 total that were 100 watts, and 120 of them were good. This fraction's easy to reduce. It reduces to 12 over 13. That fraction's not that hard to reduce. It reduces to 20 over 21. Those are more straightforward. 63 and 64 are a little harder. So for 63 and 64, I've got to do a bunch more work because it's asking me to look at 2 lines as opposed to 1 line. So 64 says, what's the probability that it's defective? And it says, given it's not 50 watts. So the part of the table I can look at is the 20 watt or the 100 watts, because those are not 50 watts. And of those, there's some good ones. There's 80 good 20s, 120 good 100s. And of the 20, there are 15 defectives, and of the 100, there's 10 defectives. And then the total, there's 95 20s, 130 100s. So I'm supposed to look at that table, that portion of the table. Now I need to add. I need to make some new totals up because I'm doing more than 1 line. So there's going to be 180 plus 120 plus 80, 200 bulbs that I'm looking at that could be good. 25 that are defective, and if I add these I get 225 total. So I need to restrict my table to this, because these are all the bulbs that are not 50 watts, and of these there's 225 bulbs and 25 of them are defective. So the probability, I had to construct a new total row because I'm looking not just at one row, I'm looking at two rows. I needed to add those rows together before I can do my probability. So the probability is going to be 25 over 225. I reduce that by 5. I get 5 over 45. I think that reduces to 1 in 9. So the answer to problem 64 is that the probability of getting a defective if you didn't pick a 50 watt is a 1 in 9. All right, so that's a bit of section 12.7. The nice thing about 12.7 is I didn't have to do any multiplying to do my probabilities, but it's a bit trickier because you had to restrict the sample space. Hopefully I did enough that you can do the homework.